Hey guys, today we're going to take a look at this 24 volt 100 amp hour lithium battery pack that BigBattery.com has for sale. So this is a pretty neat little device. They build these out of their recycled Tesla Model 3 cells. They are 4800 milliamp hour cells, I believe. So what they did was they built a 7S20p configuration and put it in this steel box. And you can see the specs here on the front. 2.5 kilowatt hour. Here's the minimum maximum voltage. The max continuous current is 100 amps. The max peak current is 200 amps for 3 seconds, and there's a variety of BMS information and thermal information here as well. And the max charging current is 30 amps, another important number to take note of. So they sent this out to me for review to let you guys know what it can kind of do and do some testing and provide feedback from my point of view as well. So anybody who's watched this channel long enough knows that I don't like to just review things, I like to tear them down and see what's inside of them. So we're going to take a look at what's inside, and then we'll take it outside and do some load and stress testing as well. But first, let's take a closer look at the device itself. So in the top right here, we have a double pole circuit breaker, and we see that it is a proper DC rated breaker, and it is a non-polarized breaker, which is good. However, one thing I noticed is that this is a 63 amp breaker, and this device is supposed to be rated for 100 amps continuous. So following the NEC recommendation of an 80% D rate for a continuous load, I would not pull more than 50 amps continuous through this breaker. We go ahead and flip that breaker on. And we've got a voltage display in the top left, and this is the voltage it came shipped with. I didn't charge it or do anything else yet, so it's at 27.1 volts. On the side here, we have a recessed Anderson 175 amp connector. And there's some more information on the back panel here. Capacity says 2,470 watt hours, 35 pounds weight. And then the charge current is 20 amps max at 29.5 volts. And that's interesting because the charge current on the back of 20 amps disagrees with the charge current on the front of 30 amps. So they actually have this thing secured up pretty well. So there is a lid on it, but it is riveted on. There are no screws. So I'm going to have to drill out those rivets to see what's inside. There are a few screws like on the front, and I see there's some on the side. I'm guessing they're holding things in place on the inside of the enclosure. All in all, this is a very nice heavy-duty enclosure. This feels like strong steel. It's definitely nice to see a lithium battery being built in a steel box like this. So that's a big win in my opinion, the way this thing is designed. It's nice and small and compact. All right, so I don't know what's inside this battery pack exactly yet. So I turned it upside down because when I drill out these couple of rivets, I want to make sure that no metal shards or pieces of metal from the rivet are falling into the battery pack inside, because like I said, I don't know what's in there. Alright, so here's what the inside of the battery pack looks like. This is the BMS. That's actually a very large heatsink on that BMS, so I'm kind of curious what the balancing current of that is. We see the individual balance leads going down to the cell, and the battery pack is that blue, it's a shrink-wrapped battery pack. We have two 8-gauge silicone wires coming up to the B-, and then we have two negative leads coming off the P- that work their way down into the Anderson connector, and you can see the Anderson connector is right here, along with the voltage display. This circuit breaker over here is where it gets a little bit of interesting though. So it looks like a double pole breaker from the front, and I mentioned it didn't meet the requirements for 100 amps. However, there is a copper bar going on each side of the circuit breaker, so they are combining both poles. So it's a 63 plus a 63 amp, which gives you 126 amps. That's definitely an interesting setup, but that does meet the 80% D rating rule of 100 amps continuous current. So this will work for 100 amps continuous current. I just want to make that clear because I did complain earlier in the video. Whether or not wiring a breaker like this is a good idea is a separate story. I don't personally have a problem with it, but over here on the right we have the BMS wire balancing leads. The leads over here on the left are actually temperature sensors, so there are two separate temperature sensors in this battery pack. And coming off the output of this breaker is a single 6-gauge wire which goes from the breaker down to the positive of the Anderson connector. So what I'd really like to do is get that battery out and see how it's connected and whatnot, but I don't know if that's going to be possible. These two screws here are holding in the tray that this BMS sits on, so let's see if we can get that out at least. So the bottom is just the same metal material as the case. I don't know if you'll be able to see it or not, but there is very thick copper bars in there. those are some very large MOSFETs down in there. So that's actually a pretty good quality BMS in my opinion. I don't want to take it apart anymore because it is live, but that's all I can see from this point of view. So down in here you can see the battery packs. There's two separate battery packs. I'm going to guess based on the size profile that this taller one is a 4S and the shorter one is a 3S, then wired in series to make these 7S 24 volt. I would like to get them out and see how the cells are wired and remove this heat shrink, but without pulling out all these components over here and all the wiring, and it's all live and connected, I don't know if that's going to be an easy task, so I guess I'm just going to leave it as is. Alright, so I've got two of them here. We're going to wire these two in series, which will give us a 24 volt battery. So we've got 27.0 volts and 27.1 volt. I'm going to leave the lid off of this battery enclosure because I want to take the thermal cam on it while I'm testing it and see what the temperatures are inside. I'm going to connect them to my Eames inverter and run a heavy load, probably the air conditioner or the clothes dryer. And I want to measure the amount of power these put out, so whether it actually meets the 2.5 kilowatt hour that it's rated, and also see what kind of heat is generated inside the enclosure. I think that will definitely be a pretty thorough test of these. Alright, so you'll need to buy the connectors that go with these since it does not come with these cables. I had to purchase this separately. It was 20 bucks plus a few change for shipping. This is actually a very nice wiring harness. This is 6-gauge silicone cable, 200 degrees Celsius insulation rating. These are generic, so this is Anderson's style plug. These are not genuine Anderson plugs. I don't care personally, but I do think it is worth mentioning. So the way this cable comes wired currently, you have plus and minus on each plug, and they're connected in parallel. So this is really intended to connect your battery bank to the input on whatever you're working with. Since I'm going to use this cable to wire these two batteries in series, I need to rewire this connector so that it's connecting these in series and not in parallel. Alright, so to avoid cutting both of these cables, I'm going to remove each of these tabs and then switch them in one of these connectors. So you'll see there's a little bit of metal down there below the contact point. All you have to do is press that metal down and then this tab will pull out the back. So I'm going to insert a screwdriver and you can pull it right out. And I'm going to do the same with the negative side. So stick it in, press the tab down a little bit, and pull it out. I'm then going to take the black lead and cut it in half at the halfway point. Like so. So now I've got one connector with a positive uncut lead and a negative cut lead. So this cut lead is going to be my negative. So then in order to connect two batteries in series, I need to take the positive from the first connector and put it into the negative on the second connector. So we'll see here we have the negative. Insert that plug. And then we're going to take our second negative cut lead and stick it in the positive slot. And then to prevent any mistakes from happening, I'm going to take the black lead that's now plugged into the positive and wrap some red electrical tape on to indicate that this is a positive wire. Just need a little bit like so, and that's good. So before we go any further, we'll just double check our wiring. We have our negative lead, comes into the negative of the first connector. The red lead comes out of the positive and goes into the negative of the second connector. Another black lead comes out of the positive on the second connector and is labeled as positive on the end. And you really have to push to get it in. I didn't think it was in the first time, and you can see it's loose, so if it feels loose like this, you know it's not plugged in. Alright, there we go. Now it's plugged in. Of course, being mindful that these ends are bare, so you don't want to make external contact here. And with both of these plugged in, we should now be seeing 48 volts, or what would technically be 51.8, since this is a 14S of 3.7 volt batteries. And we're seeing 54.1 volts. Full charge on these batteries, I believe, is 58.8. I'd have to redo the math. So we're going to take these outside and get them charged up before we go any further. Alright, so I got these batteries out in the battery shed here. And I just crimped a copper lug onto the silicone cable and attached it to my original bolt. And that goes up into this fuse disconnect. I've disconnected all of my other lithium batteries. And there is a 125 amp fuse in this fuse disconnect box as well for added safety. Both of these breakers are turned on, and I see 27.1 volts and 27.0 volts. My inverter is turned off. Everything's been switched back to grid power at this time. So I can turn the main breaker on. Now I can only charge these at 30 amps max, so I'm going to use my smallest solar array, which is the center, which is comprised of 8 330 watt solar panels and we'll just have to keep an eye on it to make sure it is not going above 30 amps. So first we'll turn the battery breaker on for that controller, and then second we'll turn on the PV input for that controller. And the controller is starting up, and it's beginning to charge. We're at 0.8 amps. It always throttles it up slowly when you first turn it on. So we're at 30 amps, it's going above 30, 32, 35. Yeah, I don't know if we want to let this go or if we want to pull a solar panel from the array and see what happens. So we're at 20p in this battery, which means there are 20 cells in parallel and one cell. So if we divide the 40 amps charging current by 20, we're putting in 2 amps per cell. Now, I don't remember off the top of my head what the 2170 cells were rated for, but I'm certain they are more than 2 amps. So even though this recommends a max charge current of 30 amps, I'm going to leave it go at 38 and just keep a close eye on it. You can see the voltage display is already up to 28.1. Alright, so we're not fully charged here yet, but the charger is beginning to throttle back because it is sensing 58.8 volts. So I think we're going to call it quits here for the charge cycle. I'm going to turn off the PV input and disconnect the battery input of the controller as well. And we see the resting voltage with no load is 29 on one battery and 28.9 on the other battery. And that comes out to 4.14 volts per cell. So that's good enough for a discharge test for me. Turn on my big Ames inverter. So I made a note, it's very tiny here, but you can see we are starting at 10.97 kilowatt hours discharge, which matches the discharge current over here. So once I turn the clothes dryer on, it's going to put approximately a 4.5 to 5 kilowatt load on this inverter, and we're just going to have to keep watch to make sure we're not exceeding the 100 amps that these batteries can push out. After this runs for a little bit, we'll come back out in the battery shed here, and I have this FLIR camera, so we'll put the thermal camera on the battery that is open and see the temperature of the various components inside. Alright, so it's very loud out here now because of this inverter, so I'm hoping you can hear. If not, I will record over later. But basically, it successfully started the dryer, and we are currently pulling 92 to 93 amps out of these two batteries. So the voltage on the first battery is 27, and the voltage on the second battery is 27 as well. So like I said, we're going to let this run for quite a while. I'm going to continue to monitor it with the thermal camera. And after about a half an hour or so of this load, we'll come back out here and do a quick clip of the battery with the thermal camera. Alright guys, so we're about 10 minutes into this test now, and you can see it is getting extremely warm. So I noticed the 6-gauge cable down here. You know, we're sitting at approximately 63 to 64 degrees Celsius on this cable. Now if you have a look inside here, the heat sink on the BMS itself is nice and cool, sitting around 41 to 42 degrees Celsius. The terminal is a little warmer, around 70. But down here, alright, this is the connection on the side of the circuit breaker. We're at 88, 90 Celsius. Oh, there's 101 Celsius, 102. So there's definitely a problem going on down there. I'm not really sure what that's about, but Alright guys, so we got about 15 minutes into that test, and this unit on the right actually shut itself down. I had my thermal camera on the circuit breaker, the top corner up here, and I was reading 150 degrees Celsius. And then about a minute after I took that reading, I was sitting here watching it very carefully. It made this click sound, and it just completely shut off with that 100 amp load on it. I don't want to say it doesn't surprise me that it couldn't handle 100 amps, but I know I was pushing it with that kind of load. However, I will say that it is very cool and very reassuring to see this BMS working exactly as it was designed with the safety measures in mind. So these temperature sensors picked up on the over temperature in this enclosure, and it shut it down with no problems at all. 100 amps, it just flicked it right off. That was pretty cool to see. So on the front label, the chassis cutoff is set at 75C. So I would say 150C is definitely greater than 75C. So with that in mind, I'm going to stop the clothes dryer discharge test, and I'm going to go turn on the air conditioner. We'll put a slightly lower load on it and see if it reacts any differently. Alright, so I have the air conditioner running. It's approximately a 2-ton unit. It's probably about 1.8 or 1.9 ton. You can see we're pulling 48 to 49 amps. And on the breaker, I'm seeing just under 80 Celsius. And I'm going to compare the first one. I'm seeing 53 Celsius is the hottest part, with the second one, and I'm seeing roughly the same temperature. So I don't believe it's a loose bolt unless it happens to be a loose bolt in both of these enclosures, which seems a bit unlikely. Alright guys, so we've been running for just under an hour and a half when you consider the clothes dryer test and the air conditioner. The undervoltage alarm has started sounding on the inverter, which is actually kind of interesting because I had never heard that going off before. You can see the inverter is reporting 43.2 volts, and we're dropping pretty fast here now. We're down to 21.2 volts. Let's see if we can leave this on and see if the BMS cuts it out at 21 like it's advertised. And the inverter has shut off. So the load disconnect on the inverter triggered around 21, so what was that, 42 volts? That sounds about right. So we know that the 45-ish amps this inverter was putting on here did cause about 1 volt of voltage sag. However, I would consider that very normal. That wasn't bad at all. 14.85 kilowatt hours minus, we started our test at 10.97, and that gives us 3.88 kilowatt hours of power. Alright guys, so I do think that was a pretty thorough test of these batteries. They finished out at 3.88 kilowatt hours between the two of them, and that comes out to 1.94 kilowatt hours per box. They are rated for 2.5 kilowatt hours. However, I think there are a few things we need to keep in mind here. First of all, if you remember, we didn't charge them completely up to, because it's difficult to hit that exact charge terminal voltage with the PCM60Xs. When you've got a lot of current charging like that, they tend to throttle down and throttle up. It would have helped if I had the battery sense cables connected from that charger directly to the battery in here, bypassing this cabling. Additionally, the inverter shut down before the batteries actually did. And if you remember, when the inverter shut down, this voltage actually went back up by a volt in each bank. So I suspect there was a large amount of loss over these cables. But I would have preferred to see thicker than 6-gauge cable. So I'm not too concerned about the capacity. I don't doubt that if we would have done the test a little better, both on the high end and the low end, we would have gotten a little bit closer to this 2.5 kilowatt hours. I really like these batteries. They are solid design. The case is solid. I like the display. I like the connectors. The connectors did not heat up at all. I didn't really show it during the test, but I kept checking them and they weren't getting warm at all. On top of that, the BMS seems to be great quality. The safety devices work as we saw. They shut off when it reached too high of a temperature. The only thing I don't like are these circuit breakers. We really should not be using 2 poles of the same circuit breaker to double the amount of current going through it. I would have much rather saw a proper 125 amp breaker installed in here, a single pole or double pole with the negative going through it. I think the biggest problem when you parallel 2 poles like this is you can't guarantee the same amount of current is going through both poles. And all the stuff you get with these considered, I do think this is a good deal. They are $855 with the discount code battery. So while one could not withstand the 100 amps as it's designed, again, if you replace these 2 breakers, I have no doubt this would withstand the 100 amps. That's going to conclude this video. This video was primarily to do a demo, some testing. I do have a project coming up in the future where I'm going to use these in a build similar to the solar generator I did, but not quite. I don't really want to say what it is yet. I still have to gather a couple more components, so it's going to be several weeks for that. But if you have any questions or comments, or you think there was something I missed, or maybe something else you want to see me test with these batteries, please let me know in the comment section down below. Don't forget to hit that like button and subscribe if you haven't. Thanks for watching.